today we'll just do the mechanistic aspect. We'll just give you rules by which to construct these KKT points and use them for quadratic programming. You don't like it. Hello? Yes. Yeah, well, okay. It says low battery now. Ooh, that's not good. No battery here. So I guess I'll have to lower the microphones up there. No batteries here. And our system administrator is out of town or not in the office today. So I'll try to rustle up something for the afternoon. Okay. If you can just send it down right now, I can put it on whenever you're... Okay. All right. Sorry about that little gap. There is no homework due this Thursday. And that was like a sort of a little bonus for you to study for your midterm that was yesterday. To compensate, I'll give you an extra long homework this Thursday, next Thursday. I just want to make sure that you all, you cover everything that I'm talking about in homework, which is better than me talking about it or Ali doing it. All right, so let's start. We'll come to quadratic programming in a moment. Let's just start with a basic nonlinear program and write down the mechanical conditions of finding KKT points. So here's the story. You want to minimize some function f of x such that you have some bunch of inequalities gi of x greater than or equal to bi for I in the set, I call this greater than or equal to. So you have a bunch of inequalities going one way. You have a bunch of equality constraints, gi of x equal to bi. I in, let's say, an equal to set, and we'll do it in an example right now so that will become a little bit clearer. Gi of x less than or equal to bi for I in a less than or equal to set. So that's how the problem has been set up. And now if you want to set up the try to find the KKT points, you need four conditions. The first step in finding a KKT point is to form the Lagrangian. And what do you do in a Lagrangian? You just take the objective function, f of x, so let's call this L of x, L for Lagrangian. You take the function f of x and subtract from it a weighted combination of the constraints multiplied by certain multipliers. So it's your sum over I in L multiplied bi times g of xi, gi of x minus bi minus summation of I in E vi, the same thing, gi of x minus bi. So for every constraint you have a multiplier minus summation vi I in G of gi of x minus bi. So then after you form this, you have to worry about sign restrictions. I'll give you a call like shooting degree. Okay, so the first thing you do is just subtract out question.
Is bi the same for all the sums?
No. For every index, so depending upon where, so let me just put down an example here. We'll just do this example that we're going to do in class. I'll write it out. Makes life a little clearer. Where did it go? So this is the problem that we're going to try to solve today. You want to minimize minus 10 minus 20 x plus 1/2 of x transpose 2 minus 2 minus 2 x. So that's this whole thing here is the function f of x. the objective function, such that the constraints that are given are x1 plus x2 is less than or equal to 6, x1 plus x2 is less than or equal to 6. I'm going to just collect together the less than or equal to constraints at one point. x1 is less than or equal to 3, x2 is less than or equal to 5, x1 is greater than or equal to 0, and x2 is greater than or equal to 0. Okay. Unlike in linear programming, here we are not making a difference between variable type constraints and main constraints. We're just putting all of the constraints together. All of these constraints, these three constraints, look like this one here, less than or equal to type. So these three, so my set L consists of the first constraint, the second constraint, and the third constraint. My set G consists of, in this case, of the fourth constraint and the fifth constraint. And my set E is empty. There's nothing there. No equality constraints. Okay? So for this example, if you want to construct the Lagrangian, what you do is you construct a multiplier for every constraint and a different multiplier for every constraint. So this particular summation in this example would look like L of x. I'm not going to write out that quadratic again. F of x minus v1 times the first constraint, which is x1 plus x2 minus 6, minus v2 times the second constraint, which is x1 minus 3, minus v3 times the third constraint, which is x2 minus 5, minus v4 times the fourth one, which is x1 minus 0, so I'm just going to put x1, minus v5 times the last one, which is x2 minus 0, so I'm just going to put x2. Okay? So a separate multiplier for every constraint. So that's what this summation says. It just says that you look at all the i's that belong to the L index, put in a different multiplier. Look at all the I that belong to the E index, put in a different multiplier. Look for all I in the G index, put in a different multiplier. E is empty there, so it doesn't play a role. Okay? Sign restrictions. The sign restrictions on the multipliers VI, these are just given by my sensible, odd, bizarre rule. So let's apply it over here, and instead of just telling you what is what, let's just look at it and then maybe you'll figure out what. So what about the sign for V1? V1 is the variable or the dual multiplier corresponding to this constraint. Whatever kind of constraints this is, that kind of variable V1 must be. This is a minimization problem. So therefore, this kind of constraint, what kind of a constraint is this? Bizarre constraint. So this particular variable in this case would be bizarre. So V1 is bizarre, which means what kind of a sign restriction would it have? Less than equal to. So V1 must be less than equal to. What about V2? All the multipliers in the set 1, 2, 3 are bizarre. So bizarre, bizarre. So V2 is less than equal to 0. V3 is less than equal to 0. What about V4 and V5? Those are sensible. Although I'm going way below the board, but I'm sure you can make sense of what's going on here. It's V4 is positive and V5 is positive. So generally speaking here, what kind of a rule can we put? Just looking at that example, you end up getting that Vi is greater than or equal to 0 for all I in G. Vi is free for I in E. And Vi is less than 0 for I in L. It's just the same rule that we were using here. So it's nothing very dramatic there. Okay? The next condition in finding a KKT point would be the so-called gradient condition. And what does the gradient condition say? It says take the derivative of this function, the first derivative of this function with respect to just the x variables, and set it equal to 0. V's are considered to be constants. They are just multipliers, they're not variables, and therefore you don't worry about them for now. So here's the condition. Take the gradient of L with respect to x variables and set it equal to 0. So let's do it over here. So we know what the signs are, so let's not worry about it for a moment. So gradient condition in this particular case, what will it turn out to be? So I take the gradient of L of x with respect to just the x variables. So gradient of f of x is what? It's this vector, minus 10, minus 20, plus this matrix, 2, minus 2, minus 2, 2, times the vector x. So this whole thing here is nothing but the gradient of f of x. Okay, so nothing else has happened. Now what do I do with this guy? V1 is a constant, so I will simply take the gradient of this function. What is the gradient of that function? x1 plus x2 minus 6. 2.
No, sorry.
Just the inside part. 1, 1. So minus V1, because that's just a constant sitting outside, times 1, 1. Minus V2, 1, 0. Minus V3, 0, 1. Minus V4, 1, 0. Minus V5, 0, 1, equal to 0. All right? So that's what the gradient condition looks like. All I'm doing is I'm thinking of this function L of x, which is actually a function of two kinds of variables, the x variables and the v variables. So when I write the gradient conditions, I pretend that the v variables are constant. They're just some constants that are there. And I take just the derivative with respect to x and set it equal to 0. Fourth point is primal feasibility. So if I want to find a KKT point, I have to create for you two things. I have to create for you a vector x and a set of multipliers v. Those put together create a KKT point. I'm writing down the conditions that I have to solve to get you this x and v. First one says, so the sign restrictions tells me that I can't just pick any old v. I have to pick v's which satisfy these constraints. I cannot pick any old x. I have to pick an x which satisfies this constraint with respect to the v's. This now is a condition that involves both the x variables and the v multipliers. They better be equal to 0. The next condition I put that the x be primal feasible. So I have to make sure that it satisfies, x satisfies inequalities or constraints. And lastly, complementary slackness, which is, I'm just going to move it up there. I want to leave this on the board. So where should I move this? Well, I'll leave it down here, but I'm just going to say it. Next thing is complementary slackness. Complementary slackness says that all of these brackets, this constraint times the vector times the variable must be equal to 0. This multiplication should be 0, that multiplication should be 0, that one must be 0, and each of them must be 0. Which means that if the bracket in here is slack, which means the corresponding constraint here is slack, then its multiplier cannot play a role. Last week, or on Thursday, we saw that geometrically, we were only interested in those constraints that were tight. We were not interested in any other constraint when we tried to find local optimality. We were only concerned about those constraints that were tight, and the way this story brings back the tightness of the constraints is by complementary slackness. It says if this is slack, which means this is not a constraint that I'm concerned about, then its multiplier must be 0. Multiplier being 0 means that constraint doesn't play a role in the action. All right? So let's work through all of these steps for this particular case and see where we end up getting. So we've done the Lagrangian, we've taken the derivative, so this is the second condition, it says. The sign restrictions we have are this one, and that one, the blue ones are all less than or equal to 0, and the pink ones, if it works, it doesn't, let's say green ones then. The green ones are greater than or equal to 0. Right? So those are my sign restrictions. So blues are positive, and the greens are negative. I flip them over, as is usual. Okay. Now, what about primal feasibility? It means that any x that I produce must be feasible. So x must satisfy inequalities. And finally, we must have complementary slackness. So x and v must satisfy complementary slackness. So in order to find a KKT point for this inequality constrained quadratic program, what we have to do is produce an x somehow, I don't care how, and a set of multipliers v1 through v5 which satisfy this condition, that condition, and that condition. All right? The big problem here is the fact that v's have sign restrictions. If v's did not have sign restrictions, life would be easy. That's one problem. The second problem is that x must satisfy inequalities as opposed to equalities. If there were equalities, that are nice. I just invert a matrix, I get a solution to a bunch of equalities. If you have a bunch of inequalities, I don't know which of them are going to be tight, which means I have to introduce slack variables, which makes life a little bit harder. Okay. One thing you should remember, and I don't know whether Ali went over this, all of these conditions, all of these complicating conditions that we have, all they are saying is that x is a stationary point. So far, compare all of this to this condition. F prime of x equal to 0. If you're talking about trying to find the minimum of an unconstrained one-dimensional problem, the first thing we do is try to get the derivative to be equal to 0. All of these conditions are equivalent to this condition. We have only found the condition that the derivative is equal to 0. And the reason we had to go through all of this mess is because we have constraints, which means that we can't move in certain directions, which have to be accounted for in how do you define this condition. Just like in the one-dimensional case, this condition doesn't tell me whether this is a local minimum or a local maximum. It just tells me that it's locally stationary. Same thing is true here. KKT point just gives you a locally stationary point. You don't get a local optimum point. So how do you go to the next step? Well, you take the next derivative, second derivative. But just as we got into a big mess trying to find the first derivative, trying to find the second derivative is even bigger mess. You have to find a matrix. In the one dimension or in the multidimensional unconstrained case, we found this matrix and we said that this is a local minimum point if the matrix has non-negative eigenvalues. Now we'll find a matrix here and say that it's local minimum point if its eigenvalues along the primal feasible directions are non-negative. I don't care about any other directions. I only care about the primal feasible directions. Therefore, all I care about is the eigenvalues along the primal feasible directions are non-negative. Checking that, you have to construct something called a bordered Hessian. It's there in the notes if you want to look at it. And those of you who are interested, I can talk to them more. But for the rest of the class, let's just say that the second order conditions are a bit messy, and we would not want to enter there unless absolutely necessary. There are well-defined conditions. If you want to know about it, I can tell you. But from practical purposes, it's not really that relevant. So we take a different tack. We'll say, well, we'll get the local stationary point, and I'm going to somehow use some properties of this nonlinear program to convince myself that that local stationary point, in fact, is a local optimum point, and more than that, it's a global optimum point. And typically what you do is add convexity. Our interest in quadratic programming typically stems from looking at portfolio allocation problems. The objective function in portfolio allocation problems is convex. So if you have somehow created a KKT point, you would have found a local optimum point. And because the function is convex, you would have found a globally optimum point. So we will not worry too much about the second order conditions, but keep in mind that all of this is simply giving you a first order stationarity condition. You have to worry about a second order condition to get global optimality or even local optimality. But we sidestep all of that by looking at convexity. Okay? All right. So now how does one solve a QP with inequalities using the idea of KKT points? So what we want to do right now is somehow I want to create for you a point x and multipliers v which satisfy all of these conditions. That's all my goal is. Once I get you that KKT point, I'm going to conclude that this function is convex. Why? Because the eigenvalues of this matrix are non-negative, and therefore this is a convex optimization problem. And if I find you a KKT point, that's a global optimum point. My trouble right now is because of the sign restrictions on the v's and the fact that x must satisfy inequalities as opposed to equalities. And what I want to do is somehow try to find an x and v which satisfy all of this by going through a series of equality constraints QPs. Equality constraint QPs are easy, as I'll show you in an example right now as we work through this, because in an equality constraint QP, the v's don't have to satisfy any sign restriction. They are free. Vi free for I in E. So I don't have to worry about trying to find a v that satisfies certain sign restrictions, and x must satisfy equalities. So that makes life very easy. Okay, so let's try to do this. This is what we started on last week, and we'll continue with that story. So what we do is we just start with a feasible point. So this is the QP that we are going to try to solve. And I'm going to let this QP be here, and I'm going to write a bunch of equality constraint QPs on this side. And the things that I want, what we want is both an x and a v. So I'm going to put the v's here. So v1 has to be less than 0, v2 has to be less than 0, v3 has to be less than 0. I just hope that I'll put them in the same order as the constraints there. So I'm just going to switch the order of constraints to make it consistent with what we have over there, so that my example and my numbers match up properly. So the first constraint basically is x1 is greater than or equal to 0. The second constraint, the way I've written it over there, is x2 is greater than or equal to 0. The third constraint is x1 plus x2 is less than or equal to 6. The next one is x1 is less than or equal to 3. The next one is x2 is less than or equal to 3. This is the order in which the constraints are appearing there. So its corresponding multipliers, v1 must be greater than or equal to 0, v2 must be greater than or equal to 0, v3 must be less than or equal to 0, v4 must be less than or equal to 0, and v5 must be less than or equal to 0. So the first step in trying to find, so what I want to do, my whole big goal at the end of the day is find an x and a v that give a KKT point. Meaning that give me a point which satisfy those 5 conditions that I have put down. And the way we're going to go about doing it is to first start off with a feasible point. So x0, the starting point, is given by the vector 2.5 and 0. So here is the point. I put a superscript, so let's put a superscript there.
You won't worry about the selection of the point?
Okay, good question. How do I get a point which is feasible here using stuff that I already know? So I don't want to solve the QP, right? The QP is tough. Yeah, in this particular case, 0, 0 will work. In general, what will we do? In this particular case, 0, 0 will work, and in most cases, just like we were arguing in linear programming, in most cases, doing nothing is feasible, meaning 0, 0 is feasible. In general, one would have to worry about trying to get a feasible point for this, but getting a feasible point, I don't care about what objective sits there. Just solve an LP. Just pick any old cost function you want and solve an LP and you'll get it. Okay? So feasible, and so in most cases that we'll be talking about, typically what will happen is doing nothing is okay, which means x is equal to 0 is feasible, which is what one could have chosen x is equal to 0. But x is equal to 0 is going to become an uninteresting problem. Okay, before I go further, let me just plot this feasible set so that we can see what's happening right now on this particular function. Here's x1, here's x2. It always lives in the positive orthant. There is 6 and 6, so that looks like x1 plus x2 is less than or equal to 6. x1 is less than or equal to 3, so here's the point 3. And x2 has to be less than or equal to 5. Let's say here's 5. There. So this polygon is the feasible region. Okay. If we were solving an LP over this, I knew that the optimum point is only going to be in one of these 5 corners. Since I'm trying to solve now a quadratic program, I'm no longer guaranteed that the optimum will be at these corners. So I have to do something better than just simply checking the corners. Okay. So first thing, I find the point x0, find all the constraints that are tight. Let's call that the set I of x0. So that's 1, 2, 3, 4, 5. Which are the constraints that are tight at that point? None of them? x2 is equal to 0. So this one is tight. Everybody else is slack. So the tight constraint is simply this. Okay? So I'm going to construct an equality constraint QP that what it's trying to do now is I'm going to have a new QP which says that the point x is the current point x0 plus a deviation d. It just becomes convenient to talk about the QP in terms of d because we would want to move from the point x0. If I computed the point x0, then I have computed the point x directly, then I'll have to figure out how far can I go, and I have to look at the difference of x minus x0 anyway, so let's just talk about d. In this particular case, the new QP would be given by minimize the gradient of the function f at the point x0, at the current point, transpose d, plus the Hessian just remains the same. The quadratic part remains the same. And let's call this matrix Q. Such that I'm only going to put the constraint that is tight. And in this case, it will say that d2, the second component of 2, must be equal to 0. So this one says only keep tight constraints. What? Okay. So what I did here is I have a function f of x. I'm writing that as f of x0 plus d. I'm just going to make a variable substitution. So instead of talking about an optimization problem in the variables x, I'm going to talk about an optimization problem in the variable d. And since this is the relationship, if I find a d, I can immediately find an x, and vice versa. So nothing really has happened. But I like d's because d can be thought of as moving in a certain direction out of the point x0. And what we will see is that later on we can't move the full direction. We'll have to stop before. So it's convenient to think in terms of d. Question?
Yeah, why did you pick 2.50? Is it just anything?
Just anything.
That's feasible.
That's feasible. Doesn't matter. I didn't pick 0, 0 for a particular reason in this case, and that will become clear to you in a moment. Why 0, 0 wasn't chosen?
Can you pick any point in the middle?
You can pick any point. You can pick point here.
None of the constraints.
None of the constraints are tight. Doesn't matter. The rules still remain the same. You pick a point in the center, find the things that are constrained are tight. None of the constraints are tight. That's fine. No constraints here. Easier problem. Okay. So if you look at this function, if you substitute it over here, you'll end up getting that this particular function can be written as the function evaluated at the point x0 plus the gradient of the function f at x0 transpose d plus 1/2 of d transpose qd. Just substitute it there and you'll get that expression. And in the homework, I'll force you to compute this and show me that this is indeed true. This part here is a constant. So if I'm trying to optimize over d, I don't care about this. That can just be dropped out. The other ones do depend on d, and they are present over there. Now, the other constraint I want is to make sure that this is always tight. So I have to make sure that x2 is equal to 0, which is the same thing as saying x02 plus d2 must be equal to 0. But this is equal to 0, which implies that d2 must be equal to 0. Right? All I'm saying is, whatever be the constraints that are tight at this point, don't perturb them. Keep them tight. So the only constraint that's tight is this guy, x2 greater than or equal to 0. So we want to make sure that if I move in the direction, I should move in such a direction that this remains tight, which means that d2 must be equal to 0.
What's the underlying reason for keeping this tight?
The underlying reason is simply that, okay, what I want to get to is this point, x and v, which satisfy KKT conditions for this guy. I don't know how to do it, but I know how to do it for an equality constraint problem. So I've created a point, and now I'm trying to look at better points which satisfy the same constraints. Whatever constraints that are tight at this point, I'm trying to find the best point that satisfies just these constraints. And then when I reach that point, I'm going to decide whether that point is a KKT point for this one or not. If it's not, then I'll do something else. So right now, all I'm saying is that I've somehow created a point. I look at all the tight constraints at that point, and then I say, okay, let me try to get the best point there is for which this constraint is tight. So at the very least, if this is a KKT point, then that point has some chance of being the KKT point, the best point for the constraints that are tight. When I reach there, I'll have to figure out whether it works or not. But for now, I have not even reached there. Okay? All right. So how do I solve this problem? By KKT. So now I want to construct the KKT conditions for an equality constraint problem.
Could you just once more explain why we needed to move to the equality constraint?
Okay. So the question is, why did we have to move to equality constraints? The reason I like equality constraints, or the reason equality constraints are nice, is because then I don't have to worry about these conditions. They can be, all of them can be free. So I don't have to worry about whether I constructed the multiplier, it has the right sign or not. The other thing is that the condition on x's are equalities, which means that whatever x I produce, I exactly know which are the set of condition it satisfies. Whereas here, I'm kind of vague. It may be this is slack, that is tight, that is tight. I don't know which of them are tight and which of them are slack. Here, there's no confusion. D2 must satisfy this, and I don't care about anything else. The only thing I care about is the second component better be 0. Don't care about anything else. All right?
So if you chose in a corner like 0, 0, you couldn't move.
I couldn't move, and that's the reason that I didn't want to choose 0, 0. But we will get into this mess soon. It's just that we'll get into this mess one step later. So I wanted to just show you the first step of what happens when you have ability to move. If 0, 0, they wouldn't have moved. Okay.
So does this mean that in this diagram we are moving vertically up?
Horizontally.
Horizontally.
Yeah. So we are sitting at this point right now. This point is 2.5 and 0. And we are just checking, in terms of geometry, we are just saying, is this way better or that way better? That's the only question. In that picture, what I'm sitting is, I'm sitting at the point 2.5 and 0. All of this mess, when applied to this particular problem, the only thing I'm worried about is, do I go forward or do I go backwards? That's all. This is just telling you a more general way of doing the same thing. Yes?
If we first choose 0, 0, why can we move?
We'll come to it in a moment. Let's just, if you can't figure that out, we'll come to it in a moment. Right now, it's pretty obvious from this we can't move. If you look at the picture, 0, 0, we cannot move. Okay, so let's write down the conditions for this. So what are the KKT conditions here? So the KKT conditions are that the gradient of f at the point x0 plus q times d minus, we just have one constraint here, v2 times the derivative of this, which is 0, 1, must be equal to 0. So this part is just the derivative, is the gradient of this objective function with respect to d. This vector is the gradient of the constraint with respect to d, and the multiplier v2 has been added. And I'm just keeping v2 because I have the memory from where this constraint came in the original QP. It's just a v there, but here I'm just putting a v2 over there. All right? Okay, and the other condition, so this is the gradient condition. The other condition I have is that I have to worry about x, this d being feasible. So I should have that, what do you call it, 0, 1 times the vector d must equal 0. This is just a fancy way of writing just this condition. The second component must be 0. So I have three variables, d1, d2, the two components of d, and this multiplier v2. Three variables and three equations, because this is a two-dimensional vector. That gives me two equations from here and a third equation from there. So put it all together, you end up getting this system of equations down there. Right here. This is what the equations would look like. 2 minus 2, minus 2, 2, and 0 minus 1 is equal to, and x1, x2, or d1, d2, and v, d1, d2, and v. This must equal the negative of the gradient. I'm putting this onto the other side, and the negative of the gradient is 5 and 25. And the bottom equation simply says 0, 1, 0 is equal to 0. All right?
Can you explain the top right part, 2 minus 2 and
So here what has happened is this, up to this point, this corresponds to that. And this corresponds to this, and the one at the bottom. So this matrix here is Q. So that's QD. This matrix down here is Q times the D vector. This vector has been put down here as 0 minus 1 times V2. Move the gradient at this point is computed to be minus 5 and minus 25. Put the gradient onto the other side, it becomes 5 and 25. And the bottom one is simply keeping track of that condition. Okay? Whenever you're solving equality constraint QP, you will end up getting a set of equations here which have exactly the same number of variables as their equations. So you can solve this. So solve this. So if you solve this, you end up getting that D is 2.5 and 0. Let me just put it over here. So you end up getting that the vector D is 2.5 and 0. And the multiplier V, V2, is turning out to be minus 30. Okay? All right. If D is not 0, meaning that the current point that you're sitting at is not the optimum point for the active constraints. I started with a point x0 at which the second constraint was active. What is this QP trying to do? It's just trying to find the best point which just satisfies the active constraints. I've dropped all the other constraints. I'm only worried about the active constraints. And what I have found is that D, this vector, is not equal to 0. If the vector d is not equal to 0, it means that you have to move away from the point x0. The current point x0 is not optimum, move away from there. That's what d tells you. If that is the situation, that we are sitting at a point which is not optimum, which is the same thing as saying d is not equal to 0, I completely ignore the multiplier here. I don't care about this guy. Don't have to look at it. It's some junk that comes about. And the only thing that I care about is, okay, that defines a KKT point for the equality constraint QP. Okay.
This would follow a recursive step.
What?
This would follow a recursive step in the sense that you go on and on.
Yes, I'm going to go on and on and on to solve my... So the comment was that, would this be a recursive step? Well, it's recursive may not be the right term, but it will be a repetitive step, sequential step. Yes?
Do you not care about e to the negative 30 here?
Because right now, the current point is not even a KKT point for this equality constraint QP. What this problem tells me is that the current point that I have sitting at x0, that's not even good for this guy. Move away from here. I'm interested in finding KKT point for this problem. Right? I don't care about that equality constraint problem. It's just there because I want answers for this problem. So in order for something to be a KKT point for this problem, it better be at least a KKT point for the equalities that it satisfies. Right now the point x0 doesn't even satisfy those. This particular problem tells me move away from x0. That's not the right point to be at. Once we get to a point where d is equal to 0, meaning that I've stuck myself into a point I can do no better, then I'm going to worry about what happens to the multipliers. For now, it just tells me to move, and I'll move. Okay, so once I've found the direction, so the first step in the story is find a direction, which we just did. And the direction we found was d is equal to 2.5 and 0. The second step is, how far can I move? So here, I have to consider the dropped constraints. So when I found the direction d, and this will come back when we talk about general nonlinear programs, when I found the direction d, I completely ignored the constraints that were slack. I only considered the constraints that were tight. But at all points, I want the x to be feasible. I want to make sure that the new point that I get is always feasible. So I have to somehow bring back the constraints that I've dropped, and here's where I bring it back. So I'm going to consider the point x to be x0, the current point, plus some multiplier lambda times the direction d. So I'm going to move in the direction d, but I don't know how far I'm going to move. And the lambda is determined by looking at all the other constraints that were dropped and find the maximum lambda that is allowable. So let's check the first one. So this becomes, in a vector form, the point 2.50 plus lambda times 2.50. Right, I'm just writing out the vector condition there. So the first constraint, x1 greater than or equal to 0, simply gives me that 2.5 plus 2.5 lambda better be greater than or equal to 0. The second condition is always tight, so I have to ignore that. Now I look at this one, which says that 2.5 plus 2.5 lambda has to be less than or equal to 6. The next one says that 2.5 plus 2.5 lambda has to be less than or equal to 3. The next one says nothing, because this component is 0 and its corresponding component is 0. So x2 is always 0, which is less than or equal to 5. All right? Okay. This doesn't give me any constraints on lambda. It just says lambda must be greater than or equal to 0. I anyway started with lambda greater than or equal to 0 because I have to move in the direction d. So this I ignore. What does this constraint tell me? This tells me that lambda must be less than or equal to 3.5 divided by 2.5. Suppose this last constraint weren't there. Suppose for the moment, and this is an important point that causes problems when you do things in practice. If this last constraint wasn't there, then this would tell me that lambda must be 7 over 5. So should I choose lambda equal to 7 over 5? No, suppose this wasn't there.
Yeah.
Yes? Just think about it for a moment. The answer to that question is no. You wouldn't take 7 over 5, but let's try to think about why we wouldn't take 7 over 5. So what did we do? We solved this QP and said that the best point there is, the point that I want to get to, is x0 plus d. That's the point I want to be at. I started scaling it by lambda because I thought that maybe I can't reach there because other constraints are going to stop me from reaching there. But I don't want to go past it. Once I get to that point, I'm happy. The only thing I want to figure out is whether I can get to the point. Lambda equal to 7 over 5 means I went past the point. That's not good. So I have to always make sure that lambda is between 0 and 1. I don't want lambda negative because that means I'm moving in the opposite direction. And I don't want lambda to be greater than 1 because it means that I went past the point that I wanted to be at. Between these two limits, I'm going to see what the constraints tell me. All right?
So this last part.
Yeah.
This lambda.
So then I want lambda to be greater than equal to 0 because otherwise if I have lambda less than 0, I'm moving in the opposite direction. Don't want that. I want lambda to be less than equal to 1 because lambda greater than 1 means that I went past the point that I wanted to be at. I wanted to be at the point x0 plus d, but lambda being greater than 1 means that I went further than where I wanted to be. Don't want that. So I want to stop at 1. But maybe the constraints tell me that I can't even reach lambda equal to 1. But if I reach lambda equal to 1, I don't want to go any further. Okay? All right. So that gives me lambda less than 7.5. This gives me lambda is less than 1 over 5, which is 0.2. Again, pictorially over here, which is the point x0. So now my new point x1 is the point x0 plus the lambda that I just computed, 0.2 times the d, which is 2.5 and 0. Everything worked out, it becomes 3 and 0. And so all I've done now is moved my point from here. This point was x0 to this point here. That point is x1. All right, I've come to that corner now. Are these two steps clear about how we, so the two things that we have done so far is the following. We created a point x, we found all the tight constraints at that point, we constructed a QP which just has the tight constraints in terms of a deviation vector d. Why? Just a moment. The construction, the deviated vector, because I looked forward and I knew that I might not be able to move the complete direction, so therefore deviation is good. Once I get the deviation vector, I look at the constraints that were not dropped, or sorry, that we didn't consider, and compute what the lambda should be. Question?
What if you had more than one value within this range? You would have picked the largest one if there was some other constraint as well.
Yes, I want to move as far as possible. I don't want to stop myself. So the only thing I want to care about is I want to make sure as far, I want to choose the largest possible lambda which is less than equal to 1. And other than that, I don't care. Okay? All right. Okay. So now you repeat the whole story again. So the story is I have to find a new direction at the new point. The new point is x1, which is 3 and 0. What are the tight constraints at this new point x1? Which are the constraints that are tight?
Second and fourth.
So second constraint is tight and the fourth constraint is tight.
Yeah, Professor.
Yes?
If you have several upper bounds for them, that you said you want to choose the biggest one. I thought you
No, the largest possible lambda that is allowed. I never said anything about several upper bounds. I want to choose the largest possible lambda that is allowed within the bounds. Okay? I don't care about, my idea is I just want to move the largest possible. Okay, so we do the find direction. So now we have to find a QP where all the constraints that were tight are going to be tight here. So the second constraint says that D2 must be equal to 0. That's coming from this. What is the constraint that's coming from there? So let's just write it in terms of the deviation. So x is equal to the current point x1 plus the deviation d. And this constraint tells me that x1, which is equal to x11 plus d1, is equal to 3. Right? I'm going to keep the current, all the constraints that are tight at the current point to be tight. But x11 here is equal to 3, which implies that d1 must be equal to 0.
Is that vector I just a placeholder, or what's the purpose of it?
Which I?
The I matrix over there where you have all the states.
I got confused. This one?
Yes.
It's just a definition. It just says the set of constraints that are tight. That's all. Doesn't really, it's just way of keeping track of what is it. So here, it just says that d1 must be equal to 0. All right? So this is something that you should keep. This is a simple pattern that should become obvious to you. What is happening is this particular constraint always would look like some A, I, D equal to 0. You look at the A matrix for tight constraints. Look at the constraint matrix, pick out the rows corresponding to the tight constraint, multiply that with the vector D and set it equal to 0. What are the rows here for the tight constraint? This particular row would look like 0, 1. This particular row would look like 1, 0. So the corresponding constraint here would simply be take those two rows and set it equal to 0. 1, 0, 0, 1, D equal to 0. Which is the same thing as saying D2 is equal to 0 and D1 is equal to 0. And I've switched the order, so I'd better put them right back in the right order, otherwise things will become a problem. So the order is important because the multipliers have different signs. One is positive, one is negative. Okay? All right. It's pretty obvious by just looking at that QP, what is the optimum D? 0. And this is why I was saying that if I started with the point 0, 0, I could not move. Because at the point 0, 0, there are two constraints that are tight. X2 must be great. This is tight and that is tight. And if I want to solve a QP with two tight constraints in two variables, it will tell me don't move. But let's keep on going. Let's do our steps, and then we'll have to figure out how do I move from there. Either I have to decide that this point, x1 is optimum, meaning that it's the KKT point, or I have to figure out somehow how to get myself out of that trap. All right, so write out the condition. The condition again is the gradient of f at the point x1 plus qd minus, let's call this matrix A sub I. So it will become A sub I transpose V is equal to 0. This is the gradient condition. The other condition would tell me that A sub I D must be equal to 0. This is the primal feasibility condition. Put all of that together. Now you have 4 equations in 4 variables, and that's what that equation looks like. Here is this matrix AI sitting here. Here is the matrix minus AI transpose sitting here. This is the matrix Q, which multiplies D1 and D2. Minus AS transpose multiplies V2 and V4, because those are the two constraints that are still active. And here is the constraint which says AI times D must equal 0. Okay? So 4 equations in 4 unknowns. Inverted, I already know that D equal to 0 will be the optimum solution, so no surprises there. So this time around, I end up getting that D must be equal to 0. And I end up getting that the V2 must be equal to what? Minus 26. And V4 must be equal to minus 4. So currently, I'm sitting at the point x1 equal to 3, 0. My QP tells me don't move. This is the best point you can find if you insist that the constraints that are tight at the point x1 should remain tight. I have done something and created for me two multipliers, V2 and V4. Now I want to check whether this point x and those multipliers V2 and V4 satisfy KKT conditions for my original QP. This is the QP that I'm worried about. That's a QP that I just constructed to help me along the process. So what about this point x? Is this going to be feasible for this QP?
Yeah.
Yes, I've always tried to make sure that my x is feasible. I found a direction at which all the active constraints were still active. Then I use this lambda to make sure that x is feasible. Okay, so this point is feasible, which means that it satisfies all the primal feasibility conditions. What about this v? So first of all, I have to worry about what happens to v1, v3, and v5. What do I put values there so that I have some chance of this being feasible? 0. 0 is always feasible, just extend it by putting zeros. All right. Now what about the gradient conditions for this? Is that satisfied? Let's not worry about the sign constraints right now. Suppose I just talk about the gradient condition for this big QP. Does x and v satisfy the gradient condition for the big QP? Yes, no, maybe? Those are the three options. Okay, so what would a gradient condition for this LP look like, this QP look like? It would tell me, take the gradient at the point x1 minus, take the whole A matrix, transpose V equal to 0. Okay? This is what the conditions would say for the entire QP. I'm not worrying about the sign on V right now. I'm just looking at the gradient condition. What do I have here? I have here that the gradient at the point x1 minus the tight constraints transpose V is equal to 0. That's what I computed. Right? And for all those V's that were not in my tight constraints, I put those V equal to 0. Right? So this particular equation is still equal to, this particular expression is equal to the expression minus AI transpose V, because here I have made sure that the other V's which are not active are 0, and therefore this entire expression is equal to this expression, which by here I know is equal to 0. All right? To summarize the story, what do I have so far? I have made sure that the x is feasible. I have made sure that that x satisfies gradient condition with respect to the v that I have created. What about complementary slackness? Would complementary slackness be true? Yes. I only considered active constraints. So complementary slackness is also true. So the only ingredient missing is sign constraints. If this v that I have created here satisfies sign constraints, I'm done. I've found a KKT point. And therefore I've found a local optimum. And therefore, because Q is positive semi-definite, I've found a global optimum. So I have to now worry about checking whether this correctly has a correct signs. So does it? No. Which one is bad? V2 should have been greater than or equal to 0. So this one is bad. Okay. So what does one do now? How do I get out of this mess? Now one uses the idea that these V's, just like linear programming, these V's are sensitivity analysis. They give me the rate of change of the objective with respect to the right-hand side vector. So V2 is the rate of change of this objective, let's call it F, with respect to B2. Now, what does minus 26 mean? It means that if delta B2 is positive, this implies that the delta F is less than 0. If I allow the right-hand side to become greater than 0, if I increase the right-hand side, because my dual variable here is negative, it tells me that the change in the objective function would be less than 0, which is good for me. I want to minimize the function. Therefore, I like to do those steps which will make sure my objective function drops. Now, what does that mean in terms of our problem here? What have we done? When we created that equality constraint QP, we insisted that this constraint be tight, that x2 be equal to 0. Increasing the right-hand side of an equality constraint is equivalent to say, let's make that constraint slack. Right? I have an equality constraint, I'm insisting that something on the left-hand side is equal to something on the right-hand side. My dual variable says that if I increase the right-hand side, then I gain in my objective function. If that is equivalent to saying I'm letting the left-hand side be strictly greater than 0, I'm allowing it to move away from 0. And therefore, at this point, what I do is from my active set, I drop the second constraint. I'm saying that the multipliers are wrong, and therefore it's better for me to just drop this constraint. Don't insist this to be an active constraint. So I go back here, and now my active set second constraint drops away, and you end up that being your only constraint. Find a new KKT point. So this here summarizes the story. So if the multiplier V is not dual feasible and V act like partial derivatives, if it turns out that FB will decrease if a particular constraint is allowed to be slack. This just tells you two different cases. The only thing that you need to remember in terms of a rule is that if you drop this, you make it better. But you should remember what is happening in the background so that you know that the logic behind doing it. All right. So I drop that constraint, and I end up getting this as the new equation. What has happened here is that the type constraints have dropped to just 1, 0. That's sitting over here. Minus 1, 0, minus 1, 0 transpose is sitting over there. You solve it, and you end up getting that D should be 0, 13, and V4 should be minus 30. Again, this D is not equal to 0, so I don't worry about the multipliers.
Could you just repeat why we dropped the V2?
Okay. So V2, so the question is, why did we drop V2? Think of V2 as a partial derivative of the objective with respect to the right-hand side vector. What it tells you here is, another thing to keep in mind is that when we solve this equality constraint QP, what we really were doing is that, I'm going to change these two constraints. What we really were insisting that this be equal. The original QP simply said that this be greater than equal and this be less than equal. When we solved the equality constraint QP, we said, well, I don't like that. Let us make it equal. Okay? I solved the problem, and I end up getting that the dual variable corresponding to this constraint has a sign of minus 26. Right? Which means that instead of insisting that x2 is equal to 0, if I had said x2 is equal to some epsilon positive, then I would improve my objective. Right? But allowing x2 to be some epsilon positive is equivalent to saying that this be strictly greater than 0. I allow that constraint to be slack. If I allow that constraint to be slack, then that constraint doesn't play a role here anymore. Okay? So those are the sequence of steps that went behind what happened there. So let me just put back the real QP that I'm after. You solve this, you end up getting V4 equal to minus 30. Now, I don't care about that V4, and here's what the whole story happens. So this is what this is something that we computed. Already lambda equal to 0.2. You drop I equal to 2, meaning that you drop the second constraint at step number 1. At step number 2, you get the direction to be 0, 13. You go through and check which are the constraints that are tight and what is the largest value of lambda. You end up getting lambda equal to 0.2308. and the new point that you get is 3 and 3. So from here, you move up, and where's my green pen? So from here, you move up to this point, and this point is your point x2, or is it, what's it called? Yeah, x3. In that label, what did I put? x3. What happened was x2 and x1 are the same, because I was not allowed to move, so I just got stuck there. Again, two constraints are tied at the point x3, so I already know that I have to drop one of the constraints. So here, if you compute for the optimum d, you get optimum d equal to 0. The tight constraints are the third constraint and the fourth constraint. The corresponding dual multipliers are 0, 0, 0. This 0, 0, 0 is just coming from the fact that those are not active constraints. For the active constraint, I got minus 20 and 10. And this has, both of them have the wrong sign, right? Oh, only this one has the wrong sign. That one is correct. So this one has a correct sign. That one has a wrong sign. So I drop that constraint. Drop I equal to 4. Compute it again. And so what I'm doing is I'm dropping this constraint now, and I'm keeping that constraint as tight. The new point x4 turns out to be the point 1.75 and 2.5. So it'll be somewhere here. So this point here, x, was it 5, turns out to be 1.75 and 4.25. So at that point, only one constraint is tight, which is that x1 plus x2 equal to 6 constraint, which is constraint number 3. So I'm sitting at the point x5. Only one constraint is tight, which is the third constraint. Now if I compute, again go to the equality constraint problem and compute what the d should be, I end up getting the d must be 0. But this time the sign of the dual multiplier is correct. So although only one constraint is tight at this point, the sign of the dual multipliers is correct. It tells me don't move. Therefore, that's a KKT point. So in this case, I found an optimal solution that is not at a corner. It's right in the middle of a face. Question?
What happens when you have more than one sign violated? Nothing, you just choose one of them?
Just choose one of them. So the question was, what happens when you have more than one sign violated? Just pick one. It doesn't really help to drop both. You can't systematically say that dropping all of them is a good idea. So you might as well just drop one. You can make rules about which to drop, but again, those rules are very specific to specific cases. All right? Okay. So let me reiterate what happens here. In the active set method for solving quadratic programs, and you'll be asked to do it one in the homework so you can get more practice about this, what you want to do is you want to somehow get to the KKT point by solving equality constraint QPs. And the algorithm that we use is the following. We start with a feasible point, we find all the tight constraints at that point, and then solve the equality constraint QP to check whether this current point is optimum for the tight constraints. If it's not, we move to a new point, find again the tight constraints, again solve an equality constraint QP, and if it turns out that that point that you're sitting at is optimum, meaning that the corresponding d turns out to be 0, then I go back to this problem, this big problem that I'm trying to solve, and check whether the current point that I have is a KKT point. And how do I check it? By looking at the signs of the dual multipliers. If the signs of the dual multipliers are correct, then I'm done. I have a KKT point. If the signs of the dual multipliers is incorrect, then I drop any one constraint which doesn't have the right sign. Go back again to the equality constraint QP, and this time I'm guaranteed to move. Why? Because of this property. This property says that if I relax a constraint which had the wrong sign, I will move away from tightness. Therefore, I'm going to move again, and I keep doing it and keep doing it until I get a point which I like, meaning d is equal to 0 and the dual multipliers are correct. At that point I stop. Question?
Because you have
I mean, you're basically assuming that the KPT point that exists will lie on the boundary, right?
No, I'm not assuming that.
You're not assuming that. So what if, for example, we're minimizing something that is convex level sets, right?
Yes.
What if that center, some ellipse or something, what if
Yes.
that center lies within that feasible region? So
That's perfectly all right, because v equal to 0 is always feasible.
No, but
So the question is, am I assuming that things will happen at the boundary? No, I'm not. The reason is this. All I want to do is the following. I want to get this condition to be true. If I look at the tight constraints, I want to make sure that I look at the rows of the tight constraint, that times v must be equal to 0, right? If something falls right in the center of this convex set, then what happens? All my constraints are slack. Therefore, by complementary slackness, none of the v's can be active. And therefore, what this equation tells me is that the gradient better be equal to 0 at that point. So all that is saying is that this implies that the gradient better be equal to 0, which makes sense. If I'm trying to minimize a convex function in the interior of a convex set, then I might as well pretend that the convex set doesn't exist. Because locally, nothing happens to it. I can move in every direction. Right?
I guess I have to understand.
So basically, okay, mechanistically what will happen is that if you come to this point, let's say the optimum solution was here. Let's say. What will happen is that you wandered from here to there to there to there. Right? Now at this point, it will tell you that the current constraint that you are insisting on being tight should be allowed to go slack. That current constraint, that it won't have the right sign. When it doesn't have the right sign, it will tell you, okay, this constraint's got to go. You drop that out, it became an unconstrained problem, and now you move in there. Okay?
How do you know if that's the direction?
Oh, no, I'm just making it up. So how would I know? I will just find again a quality constraint QP with no constraints. That's it. The story is the same all the time. You just try to solve this problem with, okay, let's just double check whether you remember your unconstrained optimization. Suppose you have this problem, D free. How will you solve the problem? I mean, so here we are trying to talk about the case where suppose I arrived at this point and I turned out that the KKT, the multiplier here, minus 15, wasn't minus 15, but was some plus number, some positive number. Then it would have told me that drop that constraint. So if I drop that constraint, I would end up getting this problem. So what is the optimum solution of this problem? What? So I put the gradient of that function with respect to d equal to 0, which is the gradient of f at the point x0 plus qd equal to 0, which tells me that d is equal to q inverse f of x0 and with a negative sign in front. Okay? And again, I have to do the same thing though. I have to make sure that I start the new point x1 is equal to the current point x0 plus lambda d, where lambda lies in 0, 1. I'm not allowed to move too far. And in this particular case, that might actually be relevant. Because what might happen is that if you just compute lambda, you will end up saying, come here. If you don't remember the fact that lambda has to be less than or equal to 1, what will tell you on the picture was hit there. And then it will tell you, go back. It's not optimum. And at least, what was it, like maybe not last year, but the year before, I had given a QP and on an exam where people forgot about this lambda equal to 1, and they kept jumping up and down. Because it'll just tell you, if you go too far, it'll tell you to go back. And then when you don't remember that, you'll go back to that point. And you'll keep moving up and down, which is not a good idea to do in an exam. Homework, it's okay.
They repeat it repetitively doing the calculations.
No, they didn't repeatedly do it. They did it twice, and then they realized this is going on. And then you have to worry about what did I get wrong, because this was a basic QP problem.
So you didn't tell them it has to be better.
No, I didn't tell them, but they forgot about it. What can I do? I'm just saying that if I tell you this story, don't forget about it. This is an important thing and it causes problems in practice. All right? Okay, so in the afternoon we'll start on the next step.
So it says that if you look at the objective function of the entire QT, it's smaller than. Now that is the function of the right hand.